Hello students, welcome to digital classes. In this session we are going to learn the most important topic and interesting topic, Euclid's division lemma and finding HCF, and also some applications related to Euclid's division lemma. First let us see the learning objectives. The learning objectives are Euclid's division lemma, finding HCF using Euclid division's lemma, applications of Euclid's division lemma. Before entering into the topic, so let us look into a puzzle. So this puzzle is, in a garden of flowers, a swarm of bees is settling in equal number on flowers. That means there are a garden with some flowers are there and equal number of bees are sitting on the flowers. How many bees are there in the swarm? That is my question. How many bees are there in the swarm? How to find how many bees are there in the swarm? We need some information. Without some more information, we cannot find how many bees are there in the swarm. So let us see some hints in this. The hints are, do you want any hints? So the hints, first one is, when they settle on two flowers, one bee will be left out. That means two flowers are there, some equal number of bees are settling on first flower, settling on second flower, then only one bee left out. Let us see the second hint. The second hint is, when they settle on three flowers, two bees will be left out. Three flowers and equal number of bees are settling on first flower, second flower and third flower. Then only two bees left out. Let us see the third hint. In this third hint, when they settle on four flowers, three bees will be left out. So there are four flowers, so equal number of bees are settling on first flower, then second flower, third flower and on the fourth flower, then there are three bees left out. Hint 4, similarly when they settle on five flowers, no bee will be left out and there are at most 50 bees. That means there are five flowers, equal number of bees are settling on each flower, first flower, on the second flower, on the third flower, on the fourth flower, on the fifth flower, then no bee will be left out. So there is no bees. So these are the hints given. With these hints, let us solve this puzzle. First let us analyze and solve this puzzle. If the swarm of bees settling on five flowers equally, no bee will be left out, which means the number of bees is a multiple of 5. So if the number of bees are multiple of 5, what are the possible numbers? The possible numbers are 5, 10, 15, 20, 25, 30, 35, 40 and 45. Why we have taken till 45? Because the number of flowers, the number of bees given at most is 50. That is why we have taken till 45 only. Next, if the swarm of bees settling on four flowers equally, three bees will be left out, which means the number of bees is divided by 4, then the remainder is 3. The numbers which we are having from previous hint was this 5 to 45. Then the remainders, if we divided by 4, the remainders are, if we divided by 5, the remainder is 1, with 10, remainder is 2, 15, 3, 20, 0, 25, remainder is 1, 30, remainder 2, 35, remainder 3, 40, remainder 0, 45, remainder 1. So if you observe that we need remainder 3. So from this there are two numbers which are getting remainder as 3. So 15 and 35, two numbers we got as remainder 3. So the possible number of bees is 15 or 35. So out of this 15 and 35, 15 or 35, 1 is the correct answer. So to find out the correct answer, let us see the next hint. So the hint will be, if the swarm of bees settling on three flowers equally, two bees will be left out, which means if the number of bees is divided by 3, then the remainder is 2. So we are having the numbers 15 and 35. If divided by 3, then the remainder should come as 2. So 15 divided by 3, then the remainder is 0, and 35 divided by 3, the remainder is 2. So we need the remainder 2 is coming for the 35 number. So therefore, what we can conclude is, so the possible number of bees is 35. So therefore, the total number of bees in the swarm is 35. Children, as of now we have solved the puzzle and find out the number of bees settling on each flower. Okay, the total number of bees are 35 we got. Let us verify the answer with the hints given. So the answers are, first one, if the swarm of bees is divided into 5 equal groups, no bee will be left out, which is translated to 35 is equal to 5 into 7 plus 0. That means 7 bees are sitting equally on each 5 flowers, then there is no remainder. And second one is, when they settle on 4 flowers, 3 bees will be left out, which can be converted to 35 is equal to 4 into 8 plus 3. That means 8 bees are sitting on each of 4 flowers. So there are 3 bees left out. The third one is, when they settle on 3 flowers, 2 bees will be left out, which is translated to 35 is equal to 3 into 11 plus 2. That means 11 bees are sitting on each 3 flowers, then 2 bees left out. When they settle on 2 flowers, 1 bee will be left out, which is translated to 35 is equal to 2 into 17 plus 1. That means 17 bees are sitting equally on 2 flowers each, then 1 bee is left out. Let us generalize this. Let the total number of bees be A, number of flowers be B, number of bees settling on each flower be Q, and the number of bees remaining be R. So we have considered A is the total number of bees, and B is the number of flowers, and Q is the number of bees settling on each flower, and R is the remaining bees, which can be translated to the total number of bees is equal to the number of bees settling on flowers plus remaining bees. That means, which we can write as dividend is equal to divisor into quotient plus remainder. Here always remainder is either 0. If it is greater than 0, it should be definitely less than the divisor, which can be written as 0 less than or equal to R less than B. Let us conclude this. For each pair of positive integers A and B, we have found the whole numbers Q and R satisfying the relation A is equal to BQ plus R, where 0 less than or equal to R less than B. Let us take one example. 4, if 4 divided by 3, we are getting as 1 as quotient, 3 ones are 3, 4 minus 3 will be 1. Here 1 is the remainder and 1 is a quotient, and that 4 is a dividend and 3 is divisor. Let us take one more number, 5. If 5 is divided by 3, 3 ones the 3, 5 minus 3 will be 2. Here 2 is a remainder and 1 is a quotient and 3 is a divisor. Let us take one more number, 6 divided by 3, then 3 2s are 6, 0 is the remainder. That means if we are taking 3 as a divisor, then the possible outcomes or possible remainders are only 0, 1 and 2. So whenever we are taking any divisor, always the remainder should be either between the 0 and B and should not be equal to B. It is always 0 less than or equal to R less than B. Example 1. Find the quotient and remainder for the pair of integers A is equal to 13, B is equal to 3, satisfying A is equal to BQ plus R. Given numbers are A is equal to 13, B is equal to 3. 13 if divided by 3, 3 4s are 12, the remainder is 1. Here 1 is a remainder which can be write as R, and 4 is a quotient, and 13 is dividend and 3 is divisor, which we are treating as A is equal to 13 and B is equal to 3. Let us use Euclid division lemma. A is equal to BQ plus R, then 13 can be written as 3 into 4 plus 1. So therefore what we can write is quotient q is equal to 4 and remainder r is equal to 1. So here you should note one thing, that always the quotient and remainders are unique. For any dividend and divisor, the quotient and remainder are always unique. With this, let us enter into the concept, that is, let us Euclid's division lemma. The Euclid's division lemma is given positive integers a and b, there exists a unique pair of integers q and r satisfying a is equal to bq plus r, where 0 less than or equal to r less than b. So what is the Euclid division lemma? Given positive integers a and b, there exists a unique pair of integers q and r satisfying a is equal to bq plus r, where 0 less than or equal to r less than b. So the above lemma is nothing but a restatement of the long division process we have been doing all these years, and that the integers q and r are called quotient and remainder. Although Euclid's division lemma is stated for only positive integers, it can be extended to all integers a and b not equal to 0. Euclid was the first Greek mathematician who initiated a new way of thinking in the study of geometry. He is famous for his elements of geometry, but he also made important contributions to the number theory. Euclid's division lemma is one of the contributions to number theory. Now let us see what is lemma means. A lemma is proven statement which is used to prove other statements. That means, what is lemma means? A lemma is proven statement which is used to prove other statements. So this lemma was first recorded in book 7 of Euclid's The Elements. As we have studied in the previous classes, the Elements book consists of total 13 books, and this lemma was first recorded in one of the books, which is book 7 of Euclid's The Elements. Euclid's division lemma and algorithm are so closely interlinked that people often call former as the division algorithm also. So Euclid division lemma and division algorithm will treat it as always closely interlinked, than that people often call former as the division algorithm also. Euclid division lemma has several applications related to finding properties of numbers. Let us see some examples of these numbers. The first example is example 1. Show that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1. See the question once again. Show that every positive integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1. First let us see the problem in visually, and let us solve the same problem with using Euclid's division lemma. So in visualization, the same problem can be converted to the positive integers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to so on. These are all the positive integers. So now I am taking that the number 1, 2, 3, 4, 5, 6 and so on. Then 1 is equal to, I can write as 2q plus 1, where q is equal to 0. If I substitute q is equal to 0 in 2q plus 1, 2 into 0 will be 0 plus 1. So 1 is equal to, I can write 2q plus 1, where q is equal to 0, and 2 is equal to, I can write 2q, where q is equal to 1. 3 is equal to, I can write 2q plus 1, where q is equal to 1. 4 is equal to 2q, where q is equal to 2. 5 is equal to 2q plus 1, where q is equal to 2. 6 is equal to 2q, where q is equal to 3, up to so on. So if you observe these two rectangle boxes, what we can conclude is that every even integer is of the form 2q, and the every odd integer is of the form 2q plus 1 for some integer q. Now let us solve the same problem using Euclid's division lemma. the question given as show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1. The solution is, let a be any positive integer and b is equal to 2. So whenever it is given as like 2q means it is nothing but bq. So always I should consider b is equal to 2. If the question is given as a is equal to bq plus r, the coefficient of q will be my b always. Suppose question is given as 3p plus 1, then I should consider b is equal to 3. If question is given 9m plus 1, then I should consider b is equal to 9. So in this case I am considering b is equal to 2, because in my question it is given as every positive even integer of the form 2q and every odd integer is of the form 2q plus 1. Then by Euclid's division lemma I can write it as a is equal to bq plus r, where 0 less than or equal to r less than b. A is equal to 2q plus r. Here I am taking b is equal to 2. If I am substituting there, I am getting a is equal to 2q plus r, where 0 less than or equal to r less than 2. Here if you observe, always reminders are only 0 and 1, because whenever we know that as per Euclid division lemma 0 less than or equal to r less than b. Here b is 2, then I should consider the integers less than 2. The less than 2 means only 0 and 1 will come. So r is equal to 0 and 1 only. So now I should solve this problem by taking two cases. The first case as taking r is equal to 0 and the second case as r is equal to 1. So let us see the first case. If r is equal to 0, then I can write a is equal to 2q plus 0, which can be converted into 2q. So 2 into any number is always a even number. So I can write a is an even integer. Let us take case 2. If r is equal to 1, a is equal to, I can write 2q plus 1. So 2q plus 1 is nothing but 2q is a even number. If I am adding a 1 number, definitely it will become a odd integer. So therefore I can conclude that a is an odd integer. With this I can conclude every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1. So this is the one example which we have seen. Let us see one more type of example in the as second example. Example 2. Use division algorithm to show that the square of any positive integer is of the form 3p or 3p plus 1. Just observe the question, use division algorithm. So sometimes question may be asked use division algorithm, or sometimes question may be asked use Euclid's division lemma. Both are same only. So whenever they are asking like this question, so you should use the Euclid division algorithm or Euclid division lemma. So in this question we are having use division algorithm to show that the square of any positive integer is of the form 3p or 3p plus 1. So let us solve this problem same like the previous problem only. First visualizing, then using Euclid division lemma. So first visualizing, the question is given as square of any number. So square of any number means I should take the square numbers, the perfect square numbers, which we all know that 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16, 5 square is 25, 6 square is 36, 7 square is 49, 8 square is 64, 9 square is 81, 10 square is 100, up to so on. We can take any square numbers here which can be written as, so 1 is equal to, I can write 3p plus 1, where p is equal to 0. That means if I substitute p is equal to 0, it will become 3 into p is 0 plus 1. So I can write 1 is equal to 3p plus 1, where p is equal to 0. Next number 4. 4 I can write as again 3p plus 1, where p is equal to 1. 9 I can write as 3p, where p is equal to 3. If I substitute p is equal to 3, I will get 3p as 9 only. Next number is 16. 16 is equal to, I can write 3p plus 1, where p is equal to 5. 5 3 is 15 plus 1. Next number is 36, which I can write as 3p, where p is equal to 12. 12 3 is 36. and 81 I can write as is equal to 3p, where p is equal to 27. That means we can write every square number is of the form 3p or 3p plus 1 only. So let us solve the same problem using Euclid division lemma. The same example I am taking here. Use division algorithm to show that the square of any positive integer is of the form 3p or 3p plus 1. The solution is, let a be any positive integer and b is equal to 3. Why we are taking b is equal to 3 here? In the question they are asked as square of any positive integer is of the form 3p or 3p plus 1. That is why we are taking here b as 3. Then by division algorithm we can write as a is equal to bq plus r, where 0 less than or equal to r less than b. So if I substitute b is equal to 3, a is equal to 3q plus r, where 0 less than or equal to r less than 3. That means here remainder values are 0, 1, 2 only, because it should come the less than 3. So the remainders we are getting as r is equal to 0, 1, 2. So in this case, for solving this question we need 3 cases. Case 1 as taking r is equal to 0, case 2 as r is equal to 1, and case 3 as r is equal to 3. If r is equal to 0, I can write a is equal to 3q plus 0. The question is square of any positive integer, so that is why I need to square on the both sides. Then a square is equal to 3q plus 0 whole square, which can be written as a square is equal to 3q whole square, which can be written as a square is equal to 9q square. So 9q square I can adjust it like a square is equal to 3 into 3q square by taking 3 as common here, and 3q square I am considering as p. Then I can conclude this case 1 as a square is equal to 3p, where p is equal to 3q square. If r is equal to 1, a is equal to 3q plus 1. Let us do the squaring on the both sides. Then a square is equal to 3q plus 1 whole square. Here I should use the a plus b whole square formula, which is a square plus 2ab plus b square, which all you know that, and which can be written as a square is equal to 3q square plus 2 into 3q into 1 plus 1 square. Here 3q square is a square and 2 into 3q into 1 is 2ab and 1 square is b square. A square is equal to 9q square plus 6q plus 1. A square is equal to, if I take 3 common from first 2 terms, then I can write it as 3 into 3q square plus 2q plus 1. So whatever there in the brackets I can take as p. Then I can write a square is equal to 3p plus 1, where p is equal to 3q square plus 2q. If r is equal to 2, a is equal to 3q plus 2. Again squaring on the both sides, a square is equal to 3q plus 2 whole square. A square is equal to 3q whole square plus 2 into 3q into 2 plus 2 square. Here I am using a plus b whole square formula, a square 2ab plus b square. Then a square is equal to, I can write 9q square plus 12q plus 4. Here I am splitting 4 to 3 plus 1. For taking 3 common for first 3 terms, I am writing 4 as 3 plus 1. Then from first 3 terms, if I take 3 common, I can write it as a square is equal to 3 into 3q square plus 4q plus 1 plus 1. And if I consider 3q square plus 4q plus 1 as p, then a square is equal to 3p plus 1, where p is equal to 3q square plus 4p plus 1. In all 3 cases, square of any positive integer is of the form 3p or 3p plus 1. So therefore, I can conclude square of any positive integer is of the form 3p or 3p plus 1. Finding HCF using Euclid's division algorithm. Euclid's division algorithm is a technique to compute the highest common factor HCF or GCD, greatest common divisor of 2 given integers. Let us find HCF of 50 and 70 using Euclid's division algorithm. Here 70 and 50 are the numbers. So first I should consider the biggest number as A and the smallest number as B. So if I take 70 as a dividend and 50 as divisor, if I divide 50 once 50 and the remainder is 20. Now the remainder converting to divisor and divisor of the previous one converting as dividend, and the 50 is now becoming the dividend. So 20 divided by 50, 22 is a 40, 10 is the remainder. Now again 10 remainder is changing to divisor and the 20 is becoming the dividend. So 10 2 is a 20, I am getting 0 as the remainder. So in this process, whenever I am getting the 0, with what divisor we are getting the 0, and that divisor is called HCF of given two numbers. This process already you know in the previous classes. Let us do the same problem using Euclid's division lemma, and which can be used as Euclid's division algorithm. The process of doing this problem is a Euclid's division algorithm, in which we are using Euclid's division lemma. That's why this process is called as Euclid's division algorithm. Given numbers are A is equal to 70 and B is equal to 50. Then by Euclid's division lemma, A is equal to BQ plus R, which can be written as 70 is equal to 50 into 1 plus 20. 70 is equal to 50 into 1 plus 20. Here 70 is a dividend, 50 is a divisor, and 1 is a quotient, and 20 is a remainder. So after completing this process, we are not getting remainder as 0. So we should continue this process until we are getting the remainder as 0. So in this step, we did not get the remainder as 0. So the continuation of that process, the divisor will become the dividend and the remainder should become the divisor. So 50 is becoming as a dividend and 20 is becoming the divisor, which can be written as 50 is equal to 20 into 2 plus 2. Again remainder as coming as 10. So we should continue the process. Again 20, the divisor of the previous one becoming dividend of the next step, and the remainder is becoming the divisor. Then 20 is equal to 10 into 2 plus 0. So here I am getting 0 as the remainder. So whenever we are getting 0 as the remainder, we should stop the process, and whatever the divisor is there, that divisor I should take it as the HCF of given two numbers. The remainder is 0 for B is equal to 10. So therefore, hence the HCF of 50 and 70 is 10. Students, try these problems by your own. Try yourself. The first problem is use division algorithm to show that the square of any positive integer is of the form 5m or 5m plus 1 or 5m plus 4, where m is a whole number. Use Euclid's division lemma to show that the cube of any positive integer is of the form 3p or 3p plus 1 or 3p plus 2 for any integer p. For better understanding of the concept, solve the worksheets. Please visit the official website of SIET for worksheets. Let us meet in the next class with an interesting topic. Thank you, children. We learned the HCF and Euclid division lemma and the applications of Euclid division lemma in this chapter. Let's meet again with an interesting topic in the next session.